to the graphing. So quick review, make sure we're on our game here. This is exponential because it has a what? Exponential has an exponent. Okay, we call that kind of dummy proof. It's literally in the name of it. Exponential has an exponent. If I want to turn this to logs, it's all about the base. Which of these three numbers is the base? 2. So this is going to be log base 2. And then what do I do with the other two numbers? Switch them. So log base 2 of 8 equals 3. Okay, and that should make sense because this says what power of 2 is 3. Okay, what power of 2 is 3? Again, this is just super, super quick. A logarithm is just another way to say an exponent. Right? Because we use the phrase what power. A logarithm is simply an exponent. All right, common logs. We use the log for common logs. And what is the base always on a common log? 10, okay? And it's of whatever. If not specified, it's a 10. Then yesterday we saw an example of these natural logs. What was the variables we used there? ln, good. And what did we say the base was of an ln? E. And we said if you forget for some reason, which by the time we do this 10 million times you won't, log has a 10 on it, ln is right under it, and it has the blue E on it. Okay, so we know their bases. All right, so we're just going to practice real quickly because going from exponential to log to exponential is pretty much the rest of the unit. I mean, there's like weeks of this. You have to be able to go back and forth pretty quickly. Log base 5 of 1 equals 0. Begin with the base. What's our base? What's the base? 5 to the 0 equals 1. These two are always going to flip-flop. When you go from whatever to whatever, it's going to flip-flop. Begin with the base. Miles, what's the base on the next one? 25 to the what power? Equals 5. Excellent. Jack, what's the next base? Perfect. So log, exponential. Exponential has the exponent. Let's go the other way. 3 to the 4th equals 81. So I'm going to start with the word log and then begin with the base, the little guy. Rowan, what's the base here? 3. So log base 3 of what number? 81 equals 4. Perfect. Rohan. Next one. Log base who? Of? You got it. Perfect. Zosha, last one here. Log base who? Of? Equals? Perfect. Okay. Now this says without a calculator. Let's see if we can talk ourselves through this. What power of 3 is 27? 3. 3 cubed. What power of 4 is 1/64? Tell me what you want in your answer. You want a negative. So how do I get from 4 to 64? Negative 4 times 4 is 16 times 4 is 3. Okay. How do I get what power of 1/3 is 27? If I'm going from a fraction to a whole number, what do I want my exponent to be again? Negative. How do I get from a 3 to a 27? Power, though. 3. So this is going to be a negative 3. Could you type all those in the calculator? Of course. We're just working on some mental math here. Mental math. All right. Skip the next page. We're going straight to the graphing section. Page 259. 259. You can just put a nice X through. Okay. F of x equals log base b of x. Now there's some stipulations. The b value has to be greater than 0. And the b value cannot be 1. X must be a positive number. All right, there's a couple stipulations here. So let's graph log x. So go to your calculator. Did I give you one? I gave you one. All right, hit your y equals. And we're literally just typing in log x. Not ln, but log. Log x. And again, what are we assuming that base is there? 10. We're going to hit a zoom 6 every time. Now, exponential. So exponentials and logs are our partners here. Exponentials went like this. It started low and grew really, really fast. Log is doing the opposite. It's starting here and growing really, really slow. It does the opposite of an exponential. Now, there's a trick on this. I want you to look. Does any function in the world just stop in thin air? No. Now, this is pixel error on this calculator. This graph does not stop. I want to be clear. Hit your trace button. The graph right here at 0, does it have a y value? So it doesn't exist at 0, but the moment I move over, it does exist. Okay? It just doesn't exist at 0, which means there's a what there? Yes, there's an asymptote there. All right, so let's go to our table. All right, so at 0, there's an error, which tells me there's an asymptote. At 1, I'm at 0. Now, these just don't happen to be really pretty numbers. Where's our next pretty number going to be? 10 is 1. Okay, Claire. So I'm not going to graph 10 million decimals in here, but I know that they're between 0 and 1, yes? So I know just by looking at it, this graph is going up here. Okay, now you can't fall for this on the exam. You're usually going to be asked to graph a log. This graph, it doesn't exist at 0, but it is going to go down forever. Is your calculator going to show that? No, don't be a fool and copy this down. You have to understand that it goes on forever. Graphs don't just stop and start in thin air. So what that means is because of that error, oops, I put that the wrong way. We have a vertical asymptote this time. So let's get that vertical asymptote drawn in. Your graph should get closer and closer, but it should not touch. Now we need the equation of this line. The exponential, I'm just going to review here, looked like this, and it had an asymptote here. What was the equation of that line? Okay, so this can't be y equals 0. Who is this? X equals 0. Vertical lines are x equals 0. Okay, so just like every exponential had an asymptote, every log has an asymptote.
The way this graph looks from going through the arrow down, it kind of reminds me of radical functions, like square root.
It kind of does, but it does go past 0 because the square root can't take the negative, so it never goes below. But you're right, it does have that same kind of shape to it. Yes, absolutely. All right, so it says the x-intercept is. Where does this graph hit the x-axis? The x-axis. At 1, yes. The x-intercept is at x equals 1. The vertical asymptote is at x equals 0. This function is, I'm looking for either increasing or decreasing. When I go left to right, is this thing going up or down? Up. So this function is definitely increasing. And concave. Have we talked about concave in any of our functions? Okay. So here's what concave means, because we're going to do this a lot in the trig unit. If it can hold water, something like this, right? You can stick water in here. We call it concave up. Up like a cup. It can be filled with water. If it's kind of frowning the opposite way, we call this concave down. Okay, it can't hold anything. So if you look at the shape of this, can it hold anything or not hold anything? No. It can't. So we call that concave down. Okay, that'll be a description to use as you're talking about these graphs. So it's increasing, but we call that concave down. It can't hold anything. All right, so they're always going to ask these domain range questions. When we hear domain, what values are we thinking? X. We're always saying min, comma, max. What is the x min? How far to the left on the x-axis can it go?
1.
Well, it definitely goes past 1. Here's the negative 0.5, negative 0.6, negative 0.7. No.
It stops right before 0.
So it can get to 0, but it can't touch it, right? So we use an open parenthesis. How far to the right does it go? Positive infinity. How about the range? So now we want to think y values. And again, it's got to be min, then max. How low on the y-axis does it go? Negative infinity. And how high on the y-axis, even though it's going slowly, what's it always doing? It's going up, increasing forever. So it's going up to infinity. Okay. So probably on those bite-sized quizzes, I'm going to have you graph two things. Let's put it at the top. A very common question is going to be to graph something like e to the x, an exponential. Okay, and you've got to know exponential looks like this. right? We said that's exponential growth. And then the next common question is going to be to graph the log of x. Okay, and we want to recognize this picture. It has an asymptote at 0, and it grows very, very slow. Okay, so we need to know what an exponential looks like, and we need to know what a log looks like pretty often. Okay, so we graph just log x. Let's change the base. How does that affect the graph? So let's go to our calculator. How am I going to get the log base 2 in? Where do we find that? Math. Look for math. Log base. Yep, look for your log base.
You can either scroll all the way down to second, or you can hit the alpha.
You can hit alpha A. And then type in log base 2 of x. And then again, just start on a zoom 6 so you know what it looks like. So we're going math, log base 2 of x. And I'll start on that zoom 6. Does it look fairly similar in shape? Okay, does it look like we stretched it out maybe a little bit? But it definitely looks like the log function, right? It's still growing very, very slowly. So go to your table, plot some points. So I think this side's real easy to get. Now we all understand if you leave it like this, do we all understand you're getting a 0? Everyone look up here. I'm not giving you credit for this. A function cannot stop in thin air. Okay? The error is at 0, which means it has to get closer and closer. You have to finish the graph, even though it's really hard to see on this calculator. You have to finish that graph from end to end. And then you have to say every log has an asymptote. And this asymptote still happens to be at 0. Not y equals 0, but x equals 0. Bless you. Okay, it is vertical, so now it's an x equals versus a y equals. All right, and make sure that goes down forever. All right, so take a moment, answer A through F, and then we'll compare in a minute. Miles, what's your x-intercept? 1 is correct. It hits the x-axis at 1. Natalie, what's your y-intercept? Stephanie, help her out. So it hits here. It is never. There is no y-intercept. It does not touch the x-axis, or the y-axis. The asymptote is vertical, and it's right at 0, so that is at x equals 0. Okay, our domain, we have to say x min to x max. So how far to the left can this graph go or get close to? 0. Does it actually hit it? No, so parenthesis, 0 to infinity, it's going forever. The range, so now we're looking at the y values, how low does it go? Negative infinity, and it keeps going up forever, so it's going up to positive infinity. Ooh, end behavior. Okay, so end behavior, we have to use a proper notation. That is, as x approaches infinity, what is f of x approaching? And as x approaches negative infinity, what is f of x approaching? So let's see. As I go up to the x-axis, the y values are headed up to infinity. That's correct. As I go out on the x-axis, the y values are headed towards... Are they stopping at 0? No, where's this graph? Where are the y values going? They're going to negative infinity. That is totally true, because we are not even approaching negative infinity. Drew, you should be up here teaching today, apparently. All right, so let's say, is x actually going out to negative infinity? No, so we're not going to use negative infinity. The farthest it goes left is what? 0. So as x approaches 0, f of x is approaching negative infinity, right? Because this actually isn't going out to the x's aren't going out to negative infinity. The farthest they go is 0. All right. Flip the page there. So now we've done common log. We did log base 2. Try natural log. So do the exact same thing. Get your natural log graph and answer those questions. So just use your calculator. Any graphing question, use your calculator. Just make sure you hit LN this time. Does it look similar? Is it the exact same? Absolutely not. Okay, those numbers, if you look at all those y values, they are not the same. But it should look similar. They are log graphs. They should all look similar. Just like before, don't make sure that graph doesn't stop. Goes forever and ever, gets closer and closer. Miles.
What makes this increase so much slower than the regular log?
So it's slower than a regular log?
Yeah, like it's
Well, the base is e this time versus a base of 10. And e is approximately 2.718. So the base is a lot smaller. All right. Natalie? Apparently I like picking on you today. I keep calling you. X-intercept. X equals 1. Y-intercept. Never. There is no y-intercept. You're on fire. Asymptote. X equals 0 is great. Domain. Perfect. Range. Perfect. All right. As x approaches infinity, where are the y values headed? Yes. And I'm going to be smart this time. As x approaches 0, since the x values don't go to negative infinity, as x approaches 0, where are the y values headed? Perfect. Okay, now the next question is just going to slightly change. Well, I'll show you what it's going to change. Can you guess what it's going to change? Very good. It is going to change the asymptote because there's a shift happening here. And we should recognize this shift. This is, again, a very common multiple choice question. Where is this shifting the original graph? Who just said that? Miles? Excellent. How do you know left for? Yes, very good. This is going to be that horizontal shift left 4. So you want to recognize that right away. So not only is it going to pick the whole graph up and move it, it's also going to take that asymptote with it. So again, we can just type it in the calculator, use that log base button. Log base 3, make sure the x plus 4 is inside those parentheses. Okay, I'm going to do a zoom 6 so I know what it's going to look like. And it looks exactly like we said left 4. Now notice it's not crossing at 4. Okay, I want you to think back to this. What is the what is the x-intercept for all these graphs? The x-intercept was 1. So when I move it 4 left, it makes sense that it's at 3 instead, right? Okay, so let's go ahead and get that graphed, and then let's answer the same questions off to the side there. So take a moment, get that graph. It does not stop in thin air. It has an asymptote. Logs have asymptotes. Exponentials have asymptotes. Again, as I look at this table, where's that error occurring at? -4, which tells me that's my asymptote, right? Make sure that asymptote is right at -4. And that graph is going to get closer and closer, but does not touch. Okay, we're getting closer and closer, but does not touch. Maybe a few more seconds to answer those questions if you haven't. Vinny, what's your x-intercept?
-3.
Love it. X equals -3. Stephanie, what's your y-intercept? 1 this time. So we definitely have a y-intercept this time, right? We can look at it and see it's crossing at 1. Miles, our asymptote.
-4.
Just what equals?
Oh,
X equals -4 because we're vertical. Excellent. All right. Rowan, our domain. Yes, it would. -4 to infinity. So the closest to the left we can go is -4, but we don't hit it, so we're going to use that parenthesis to infinity. Yeah. Oh, it wasn't exactly 1. I was just taking her word for that. The what? Stephanie, I'm taking your word for that again. All right. At 0, it's 1.2619. You just write a few decimals down. It'll be multiple choice for the most part.
Does it really matter?
Oh, yes, it matters. It's not exactly 1. Our range goes from where to where? Yes, negative to positive infinity. All right, so now our end behavior. As x approaches infinity, where is f of x? What's the y value headed towards? Infinity. All right, now, can I use negative infinity here? What number do I have to use? Good. It's only getting closer to -4. As x gets closer to -4, the y value is getting closer to negative infinity. Okay. All right, so just watch that -4 there. All right, vertical asymptotes. Yes, ma'am.
Why is the y-intercept between 2, 6, and 8? Because that's what it's at 0.
Correct. When the x value is 0, the y value.
What's the first place that it touches the y?
Exactly, that's your y-intercept. All right, so if I look at example 3 here, this shifted me left 4, we said, right? Miles was all over that, left 4. And where was my asymptote? At -4. So based off that, where does this shift my graph?
Left 7.
Left 7. That should tell me my asymptote is at, more specific, more specific.
-7, 0.
x equals -7. We need an equation. All right, now be careful with the next one. Where would my asymptote on this one be? I think I hear it over here. Why 3?
I checked my calculator.
You checked your calculator. All right, we use the calculator. Rohan? Yeah, so you just basically want to set this equal to 0. So 2x equals 6, x equals 3. Okay, so if we solve that, now again, the backup way that we're never going to miss is we're going to graph it in our calculator and like look at it, right? Like you should never miss this question, but this is how you get it. How about this one without looking on the calculator? So x equals 4. Okay, x equals 4. And as just a quick review down here, I'm going to ignore the b for a minute. Let's talk about these two shifts. Where is this c shifting me? So this is my horizontal shift. If it's positive, it goes to the left. If that c is negative, it goes to the right. And where does this d, when it's outside, shift us? Up and down. So this is my vertical shift. If it's positive, it shifts up. If it's negative, it shifts down. Okay? And again, you really should never miss one of these questions because you really can type them all in the calculator, right? A graphing question we shouldn't miss. Oh, Jiminy Crickets, there's more. All right, turn the page. Describe the shifts and state the vertical asymptote. All right, so let's take a look at this equation. Think first. Think first, think first. Write down your two shifts. Where are we moving this function? Think first, write them down. It's the stretching of it. Yeah. So it's more of a stretch or a compression. It's not going to, it's not the trans part. It's the dilation part of it. All right, Eli. I don't think you can get away being this quiet. Love it, love it. Left 10, down 44. All right, how about the vertical asymptote? Where is the asymptote sitting? Negative what? On this guy? Not -4. Why -10? Well, we move the graph. So think about this, right? The asymptote, it starts at 0, right, when we graph a log. And all we did is we picked it up and moved it 10 over. So the vertical asymptote should be at x equals -10. Notice it's going to be the same as your horizontal shift. And again, now if you didn't catch that in your head, you're just going to throw it on good old trusty calculator here. Letter B. Who haven't we heard from? Emma? Right, 8. Are we moving up or down? Stay the same. And where's our vertical asymptote? X equals 8. Perfect. X equals 8. Letter C. Grady, right in front of me. I haven't even bothered you all day. All right, Grady, where are we going?
Left 5.
Left 5 and
Up 7.
up 7. And where is your vertical asymptote?
-5.
X equals -5. Perfect. Okay, so now they want you to put the information into log base 3 of x. So let's put log base 3. How am I going to shift this 3 to the right? Okay, just like this, x minus 3? In parentheses. The parentheses tell me that I'm shifting left or right. And if I want 4 down, where would I put that? Outside -4, right? So inside is left and right, outside is up and down. We got the idea? All right, flip the page. Oh, there's only 4 questions. Look at that. We've got 10 minutes. Oh, did we talk about... Yeah, you can graph those and look at them. All right. Well, there's 4 questions, but this one has 8 in them. So take your time. You're going to graph here, state whatever it asks you to. And then this one's asking for the domain and the vertical asymptote. Yep. we are doing page 263 and 264.
Okay.
That is it.